Uh, Good morning, everybody. So the last lecture, I think it was too messy. So today I'm going to kind of review um, and what we need from the Hilbert scheme in the last lecture. So let's. Okay. So just for the sake of uh, just a moment. Okay. Have to turn. So, just for the sake of recording the page of the last lecture in the in this lecture, so it become a kind of mess. I start talking a lot of things, and even I didn't put in the YouTube because I think it was not in a good format. So let's uh, this one. And this one, then we did this. Just a moment, what I'm doing. No, I am in the wrong direction. Uh, I just okay. Uh, okay. Anyway, today I am going to again talk about Noether-Lefschetz theorem. Uh, Last lecture it was 17th lecture, but today it will be again 17 because I am going to repeat a few things. So, what is the Noether-Lefschetz theorem? For a generic surface X in P3, any irreducible curve inside X is of the form X intersected with Y another surface. In other words, all the curves that we can write, maybe let's say, so X is given by F equal to 0, X1. X1, X2, X3 equal to 0. Then the only way to produce curves is just add to the equation of F another equation G equal to 0. And this is for generic surface. Let's again remember the thing that so I will take this T space, homogeneous polynomials of degree D. So in this case, X will be X0, X1, X2, X3. And usually one has to cut out singular surfaces. Later we will see that singular surfaces corresponds to some discriminant equal to 0. So anyway, this guy, this homogeneous polynomials is just some C to some number n, and then we cut some discriminant equal to 0 from here, so that we get smooth surfaces. So generic means that at the end we remove enumerable, let's say generic X. It means that X F outside an enumerable um, enumerable a union outside a union of an enumerable set of algebraic algebraic, let's say, proper subsets of this T. So this, since it is enumerable, it can be dense. For example, this can be, say, this let's say, this means that well, let's maybe I fix also another notation: x f equal t x t. At the end of the day, I will use these notations to, when I have a t on t, in any case, t represents some x, t is given by f equal to 0, and the notation t, and at the end the surface xt. So but then these two notations are the same for me. So what so genericity will means just that t minus union I equal to n until infinity of some ti algebraic subsets of t. So one remark that at the end, this ti can be dense in t. Okay, and in our way we will understand what are these ti's. Last lecture I talked about this Noether-Lefschetz loci and so on, but in the proof of Noether-Lefschetz theorem we will see what are these ti's. Okay, so let's try to say the idea of the proof. Okay, so first, for this one, okay, there have been a lot of attempts to prove this theorem, and there are a lot of intuitions going on also. And if you want, maybe if you want to present your window. So in chapter 14, I have gathered in the introduction some history of the of this theorem, but so have a look to this this chapter. So let's go to the idea of the proof. So what we first need is the concept of Hilbert scheme of curves in P3. And okay, so but I think it would be we would waste a lot of time if we want just to introduce these things exactly. And actually, there are a lot of open problems in the Hilbert scheme of curves in P3, and there are many in literature. But let me tell you what exactly we need from the Hilbert schemes. So HGN curves set of. So as I said, today I will repeat a little bit whatever I did in the last messy lecture, which is not in YouTube. Set of genus G and degree n curves in P3. And of course, you can also do in general, but let's just stay in this set and the context of curves. So the first idea is that this has this HHN has structure. Maybe let's write into is an algebraic variety. So this is one has to explain what this means, but because here we understand it as a set, but suddenly I say that you can look at HGN as a variety, and it means that it is given by polynomial equations. And actually, something more, we have, let's say, we have the variety, let's say write calligraphic C. So actually we have a subvariety of P3 times this HGN, and such that the projection, actually I need this projection. So I have from C to HGN, I will call the projection P. And okay, and the fiber over, so let's again by abuse of notation, let's write this one over the curve. So you remember that the fiber of P over, let's say, the curve C is the C itself. So in order to make a rigorous statement, one has to really go to the construction of Hilbert schema and so on. But at the end of the day, to what we will need exactly is that we will have a family of curves. So just take in mind this one. We have a family of curves over HGN such that all curves of genus G and degree n in P3 are fibers of this. And in some sense, there is no curves missing in this family. Okay, so this is something that that must be done rigorously. But let's keep this intuitional version of the Hilbert scheme without too much going into construction. And maybe before going to the proof of Noether-Lefschetz theorem, let me say that this exceptional component that I was talking about. So so NLGN. So the Noether-Lefschetz loci of genus will be what? This will be the image of which map? First of all, we have to consider, let's say, surface X and the curve of genus G. So this will be in T times HGN. I will take a surface and the curve such that the curve is inside the surface. So it will turn out that I have an algebraic variety. And when I project this one to T, then I will take this image, and this means that another Lefschetz loci of genus G and the degree n correspond to surfaces of degree D containing a curve of genus G and degree n. And something that I have to a little bit be careful. At the end, I don't want complete intersection. Removing, so that here I have to say one has to remove of curves, let's say C, which are in complete, they are complete intersection with another surface, the one that is stated in the Noether-Lefschetz theorem. Curves of the form Y another surface. And and yeah, so this so now the Lefschetz theorem, for this reason, in the last lecture, I introduced this HGN tilt, but anyway, maybe just write it here in letters. Another Lefschetz theorem. NLGNs are proper subsets algebraic. Being algebraic is trivial, but the properness is the proper algebraic subset of T. So so none of these NLGN can be the whole space. So and again, well, there was some confusion in the previous lecture. I think let's just skip some details, and at the end, from all this, what I need, the thing that I need, so okay, so what I need, just imagine that the Noether-Lefschetz theorem is not true. Okay, if Noether-Lefschetz theorem is not true, what this means that for any surface X contains a curve C which is not, let's say, complete intersection. In the complete intersection, in this sense, in this sense. Okay, so but the point is that okay, any surface will contain a curve which is not complete intersection, but we want to choose this to these curves in a continuous family. So if I jump from one surface to another surface, maybe I say what is the role of the Hilbert's scheme. So this means that at the end, let's say this T, and then I will have xt1, let's say, and then I have parameter x2, xt2, and how I can choose here by this by this hypothesis, I can choose the curve ct1. Here I can choose the curve c22, but we will use all these Hilbert's scheme stuff in order to say that this family of these curves can be chosen continuously. So then here, then I have to put the points. What we will have for we can okay, maybe I first time. So N L at one of NLGDs will be so dense in T. So okay, so it is natural to expect that okay, if the Noether-Lefschetz is not true, this one of these NLGNs will be Zariski dense. in T because it is an algebraic variety. So, and then what actually we'll need from here, we have a family. Let me write explicitly. So for this statement, I will need locally. So let's write T around some point T0. So this means that a small neighborhood, a small usual neighborhood. When I say usual, it means not Zariski, the classical topology. Usual neighborhood of T0 in T. So that means that locally we will find a family. We will have this. This will be the family of my surfaces. I will have this subvariety. Let me explain, and then I will have this this map also. Let's put it this alpha, beta, alpha minus 1 t will be xt, beta minus 1 t will be a curve t, curve will be inside ct. This will be a curve of genus G and degree D, degree n, sorry. Anyway, and remember that this is the whole parameter space of surfaces. So this means that we at the end we will get if our family of surface, okay, they are parameterized by T, and also a family of curves inside xt. And this is in order to make this, for example, from here to here rigorous. Then we will need the language of Hilbert scheme. So moral of the history. If the nodal Lefschetz is not true, then we will have a family of the full family of surfaces locally will contain a family of curves. And from this one that we want to get into contradiction. And the CT, so remember that at the end of the day, here at GN, I have removed the, one has to remove, let me put this HT until here. This means that from the Hilbert scheme of genus G and degree N curve, we have removed this complete intersection curve. This will correspond to an irreducible component and so on. Anyway, any questions so far?
So just a question. So you consider the Hilbert scheme of curves and also the one of surfaces?
No, the surface is easy. It is just the Hilbert scheme of the surface is just this polynomials of degree.
Yeah, because they are hypersurfaces.
Yeah, they are hypersurface. So the hypersurface Hilbert scheme is just the parameters of the polynomial.
Yeah, no. Okay, it's clear. Right. Thank you.
So the language of Hilbert scheme becomes very useful when you want to talk about the parameter space of varieties which are not complete intersection, because when they are not complete intersection, you cannot choose in a unique way the generators of the ideal of the variety. But for example, the Hilbert scheme of a complete intersection is very easy to describe. I mean, it is just one can describe it by homogeneous polynomial. Anyway, the moral of the story is that I have, let's say, this T0, and I have for any point near to T0, I have this surface xt, and then there is a curve, and actually the curve can be singular, ct. So the next step that it must be made rigorous, but I think when one makes the things rigorous, then one also loses the joy of doing mathematics. I don't know. So passing from CT to the homological class. then I will also denote it by. So I think it is well, one can make it more rigorous, but the idea is that I talked about Picard-Lifshitz theory, monodromy, and so on. So this means that at the end of the day, CT1, CT2. Let's so if you, for example, if you take let's say T and T tilde, CT is the monodromy of CT tilde along any path in T's. And this any path, actually it is for this I need that I have here the usual topology which connects T to T tilde. So this means that anyway, then I have this like this xt tilde and then the curve. So the point is that my curves can be singular and so on. And since this T0 is simply connected because this can be a ball, then I can take any path. But in order to make really, if you want really a rigorous proof, then one has to start applying a kind of Ehрешmann's theorem. Anyway, I have to say that Hodge theory is a kind of messy theory. If you want to do modern Hodge theory, which has nothing to do with all this topological idea, it becomes more rigorous. But the point is that it is sometimes good to mix with this topological idea. But once you mix with this topological idea, then you lose a little bit rigor. But anyway, just you have to try to convince yourself that family of curves will give me family of topological cycles, and these are one is the monodromy of another. Okay. So once I get this one, then okay. So remember that remember last time we defined the Hodge cycle. So integration over curves of F2 of H2 theorem xt was automatically 0. This will and if you remember well, this F2 is just H0 H0 xt 2 form, omega 2 xt, and this is global holomorphic or algebraic 2 forms in xt. And basically this is true because when you restrict holomorphic 2 form over a curve, there is no 2 form over a curve, so it must be identically 0. At the end, you just integrate 0 over the curve, and then you get 0. And I remember that this was the beginning of the Hodge conjecture, and so this means that the first indication for the Hodge conjecture is something purely trivial. Okay, so let's go further. So next, what I need is the description of the Hodge filtration of the surface. And let me so the next is before going to this one. So the idea would be that these guys, let's say, okay, maybe let. So I will need to describe the Hodge filtration here. For this one, I will use Griffiths' theorem, but let's first write Guyson sequence. Remember that we called also here Leray, Tam, Guyson, which was basically the consequence of Leray, Tam, Guyson isomorphism, but it is sometimes also Guyson sequence. Of which pair I have? Okay, from now on I will use arbitrary dimension. So in our context so far, it has this n has been so far equal to 2. So I will consider surfaces of degree d and dimension n. So I will write the Guyson sequence of this guy inside Pn plus 1. So let me try to write it. So I will have Hn plus 1. I will write both in homology and cohomology. Tn plus 1 minus x. Okay, let's write minus as slash. And then Hn around x. This will go to Hn plus 2 Pn plus 1. Maybe first I write it and then I will need in the homology also Hn plus 2 Pn plus 1. In the homology, the Hnx Hn plus 1 Pn minus 1 minus x and going on. Okay, so this is so remember that what has happened here. Remember that here states we have Hn plus 1 Pn plus 1 with boundary in Pn plus 1 minus x, I think so. No, just that one. No. Here we have Hn plus 2 actually. Okay. Hn plus 2, Pn plus 1 with Pn plus 1 minus x, the boundary, and the guides in Tom Leray guides on isomorphism was that this is isomorphic to this one, and then we substitute here in the same thing in the cohomology. Okay, so this is this we call this the residue map. Later we will in the Griffiths theorem we will discuss this map in more details. This we call it sigma. Let's call it sigma. And let's the homology. Let's write it. I will use the Ram theorem. So let's write the homology over Q with coefficients in Q. Okay. I need to describe the Hodge filtration of the hypersurface. So what we will do it? We will describe the let's say the Ram homology and the kind of Hodge filtration there. And maybe let me what we need. So first, Hn Atiyah-Hodge theorem. So this is the complement of a hypersurface in Pn plus 1 is an affine variety, and Atiyah-Hodge theorem tells us that its the Ram homology is given by algebraic differential forms. At the end, it is not difficult to describe differential form here. Hn there Pn plus 1 minus x any omega is given by omega, it will be equal to, it will be polynomial capital omega, or maybe let me, okay, let's write here and then we fk. So p. So let's explain. Omega is this xi, capital omega is, in the introduction of the Griffiths theorem, we will discuss this once again. Xi dxi hat. So dxi hat is the wedge product of all dxi's except all dxj except this dxi. And so this I have written this guy in affine coordinates. So at the end, k degree of f, which is d, must be degree of p plus, and the degree of this guy is n plus 2, and p is homogeneous. Anyway, in the Griffiths theorem, we will a little bit explain this, but it is at the Hatch theorem at the end will imply that any algebra, any element in this de Rham cohomology is given by some algebraic differential form with pole along f equal to 0. Okay, so what I need else? Okay. Maybe before going to the next page, so let's remember this one. So let's for this one, let's just consider our context n equal to 2. N equal to 2. So n equal to 2. So this is actually isomorphic to z. This is the h. Well, for n equal to even, this will be z, and then for n equal to odd, this is 0. But in our case, this will be z. Anyway, this is what we have here, and here also we have something similar. Actually, it is h n. It will be decreasing hn plus 1 theorem, n plus 1, and at the end of this guy and this guy, they are 0 or just one-dimensional object. So the cohomology of the complement of the hypersurface up to 1 dimension is just the cohomology of the x, and we want to use this property. And okay, so now I can describe the de Rham cohomology here. And even so, if I don't know hypercohomology, remember that this guy is given for us by hypercohomology. Even so that we don't we may not use hypercohomology, we can capture the cohomology of the hypersurfaces by just taking the residue, understanding the residue map applied to this kind of differential forms. And actually, Griffiths did this one even without taking care of all these Grothendieck's hypercohomology stuff. So basically, for the hypersurface, we don't need for the moment the language of hypercohomology. Okay, so remember that here we have Hodge filtration. So I will here introduce the kind of Hodge filtration here. So maybe I write here hn plus 1 de Rham pn plus 1 minus x. There was this residue map Hn theorem x. Okay. So again, from the Griffiths theorem, that from the next lecture we will focus on this theorem, we need this one. P, this Px, the element Px omega if, so polar order 1, these elements, which I said that now they are here, maps to Fn Hn theorem x, and actually these maps, this is an isomorphism in this case. So let me write here how I write it. So the collection of these differential forms, so so degree p plus p homogeneous degree p plus n plus 2 must be degree of f, which is d. So the collection of these differential forms, their cohomology class will be mapped isomorphically to this one. This means that at the end, how to capture this this piece of the Hodge filtration, it is just by considering this differential the differential form. Okay, so as I said, in the from the next lecture, for 2 or 3 lectures, we will focus on Griffiths theorem. Today, I just want to use it in order to prove the Lefschetz theorem. So what we will reach, maybe I make again I've written back to my notation. So where was my cycle? My cycle was here. So it was delta. So this was delta t. So let's just put t divided with the family, put ft everywhere. So, and sigma, and so I will consider this sigma delta t. Yeah, so which will be here. Okay, so our hypothesis will be translated in this one. So maybe I make a picture. This is Pn plus 1. Soon I will go to n equal to 2 case, but most of the things can be written in. So delta t was here. Remember that this in this Gaussian sequence, we were just thickening delta t, and we will getting this sigma delta t. And well, using this part of Griffiths theorem, we land on this that all these integrals are 0 for all t in a neighborhood, in some small neighborhood. Okay. Okay, so far, any question? We are almost getting to the end of the idea of the proof. Actually, this proof is mainly due to Griffiths, but he doesn't write in this way. He writes in the languages of infinitesimal variation of the structure, but using the languages of integral, it's possible to avoid this infinitesimal variation of its structure. Okay, so we reach to this that all these integrals are 0, and next it comes the most another interesting part. Let's write f. So f is basically t alpha x alpha monomials. So monomials so anyway, if we have maybe let me say, okay, even independently of this, maybe I have to make them to remember. All these functions, independently of the cycles also, it doesn't matter. These are holomorphic functions in T. So let's just stay in a small neighborhood of T0. And this is, we have a lot of integrals in mathematics. At the end, the integral depends on parameter. Here also you see that our parameters are inside F. If it is basically, why I use the notation T. So this, my T notation was basically this collection of these T alphas. And integrals depends holomorphically on the parameters. So what we have as our hypothesis, we have a lot of holomorphic functions here, which are identically zero. So the next step is to make this derivation. P omega f. So this is this, my integral is identically zero. But by this simple rule of, whenever we are in a calculus, we have integration, we try to take the integration inside. And at the end, it turns out, whenever the course becomes a little bit more period or integral stuff, then one can see all these things in a better way. So we just make the derivation of this guy. So you remember that T alpha is in the denominator. So this means that we will use the classical derivation of a fraction. And so what we'll have here, just a moment, it will have, so the derivation of f with respect to T alpha is x alpha. We'll have this x alpha P omega. Let me see if we have sign. I think, well, up to sign level, we have a sign also here. Okay. Anyway, if this integral is identically zero, its derivations is also identically zero. In particular, all these things are zero. And we will do it for further. Make more derivations. So remember that f is in f I have put all the monomials of degree d, because this f this family of curves that I found, this family of curves that I found, they were present in all hypersurfaces. This means that I can this T alpha are all the coefficients of all monomials of degree d. Anyway, if we make all the derivation, we will conclude. So here, the idea is that here we can have an arbitrary, maybe I write in this way. This will be identically zero, and this will imply that at the end, p tilde omega, all these integrals are zero. F sigma delta t, because anyway, you take here all monomials of proper degree. Here you will have your all monomials of degree d, and you can make the sum of linear sum of all these monomials, and then you can get again let's say degree for all homogeneous degree p tilde, let's say degree omega. Degree omega is n plus 1, in this case 4, it is 2 degree f. So the conclusion will be that making further derivations will imply that all these integrals are 0. I mean, again, Px is homogeneous of degree such that the degree of the denominator is the same as the degree of the numerator is the same as the degree of the denominator, and so on. And yeah, we are almost done. So, but by Atiyah-Hutch, what we will conclude that by Atiyah-Hutch, all these differential forms, they generated the Ram cohomology of the affine variety. So Atiyah-Hutch will imply sigma delta is 0. So in order to avoid torsions for the moment, just let's take so in our context it is hn plus 1 pn plus 1 minus x, and remember that at the end we ended it in n equal to 2 case. And let's put the rational coefficients. Anyway, we get the conclusion that these cycles are 0. Okay, and once we do this one, we are almost done, not wholly, because there will be some more details coming. Okay, so far what we have done, this guy here becomes identically 0. And so sigma delta is 0. So this means that delta t is in the image of this map. So let's write this one also. This will let me show. Delta t is in the image of which map? Hn plus 2. So let's put it n equal to 2. N plus 2 Pn plus 1 Hn xt. Okay, so well, so again, as I said, let me emphasize that I don't want to get bothered with torsions. So let's remember that these are our Q. Okay, so delta t was here. So what is the generator of okay, so we have what is the generator of this guy? And in the case n equal, let me put from now on, let's put n equal to 2. H4. So the generator of this guy, what it is, by classical topological argument, we know that this is this is P3. So we just take P3, P2 inside P3, and this is given by this one. And so for a P2 inside P3, and remember that this map, intersection map. So this means that at the end, let's say this P2 goes to P2 intersected with xt. Okay, so what is the conclusion? So delta t is a multiple. So this is just one-dimensional object, and so this means that delta t is some multiple with rational coefficients. Let's say a b p2 intersected with xt. So maybe I make another picture. So I have x, I have my P2 inside P3, and I have made the intersection P2 with the x, and then I have this this in P2 intersected with x, x or xt, whatever. Okay, so let me see. Okay. Anyway, so we reach to this part. So anyway, what we have is that a. So let me call this one CT. Oh, sorry. This was already, we called it CT. And this is, let's call this one, let's say, another name, C tilde T. So C tilde T is the complete intersection, but CT is not complete intersection. So A C tilde T minus B CT is, this homological class is 0. So we get to factor homological class of A. So A and B, let's say integers with A and B not equal to 0. Okay. So actually A can be, delta T can be 0. So let me say, no, because this, maybe let's just A not, B not equal to 0. Okay. Homological class of A C tilde T minus B C T is 0. And we're almost done. Then we have to conclude. We have this must imply that C tilde is also a complete intersection. A complete intersection. So this part we have to explain. I think, let me see. I think in 7 minutes I can finish this one. Okay. So the last page. So if you'll have a look in the version of Lifshitz 1-1 theorem that I have put in my book, for surfaces in P3 homologically 0, it means algebraically 0. So let me explain this one. Anyway, we had this, let's say, AC tilde B CT. This was its homological class was 0. So here what I mean, homological class this imply that A in our context, algebraically 0, this means that A tilde minus BC tilde is a divisor of a rational function in xt. And yeah, so let's actually in our case, let's assume that A bigger than 0 because we just needed the rational number A over B. Okay, let me so if again I have to explain this this implication. For this one I will present a part of my book anyway, and once this is done, we have already done, because first of all this will imply that B cannot be negative, otherwise we will have a positive divisor, because A is positive and then B will be positive, so the B must be necessarily positive. And it will at the end what we'll have a rational function. Then rational function and xt, they are just of the form fg restricted to xt, fg homogeneous polynomial of the same degree. And then this means that f equal to 0 intersected with xt will be the ct tilde. Let me actually I have to write in this way. I have to be a little bit be careful if the things are irreducible or not, but let's up to these details, maybe let's write in this way. F to the, let's say f equal to 0 will be A and then B here, and then G equal to 0 intersected with xt will be ct. At the end, we will reach to this to the fact that the CT itself is also a complete intersection with another surface. But maybe just focus on the non-trivial part. From the homological equivalence to 0, we have to conclude that this divisor is algebraically equivalent to 0 in the sense that it is the divisor of some rational function. So these details they are not so hard to do. So for this part, we have to go to to part of the Lefschetz 1-1 theorem that I didn't make any focus on it. So let's try to go to there. Okay. Let me try to. So here I have put the both topological and the homology class of the so this is theorem 9. Actually, in our case, we will need that h1 xt. This is 0. But anyway, this is theorem 9.2. So let's go to the theorem 9.2. For divisor in a hypersurface x of dimension, algebraic dependence and homologic dependence in x are equivalent. And the proof is not really hard. The proof uses the fact that when we write this long exact sequence of this, what was the variable, this short, this exponential, this one, then we will have this one. For hypersurfaces, well, we will use this fact that this h1 xot is equal to 0. So in some sense, two lines bundled, we will conclude that two line bundles are the same if and only if their chain classes are the same. And yeah, so again, just to mention that the end part of the proof is not so difficult. Okay, I think for today it is enough.